the dot product or the scalar product. This is an operation that applies to vectors. Okay, so it has three commonly used names: inner product, dot product, or scalar product. Dot and scalar are the most commonly used ones that you'll come across. Occasionally it's called inner product. So it's defined as the scalar product of the two vectors is the sum of the products of the corresponding elements. And the symbol to denote that is a dot. Do not use a cross. There is another thing called later on called the scalar or vector product, which we'll cover, and it uses the cross. So it's very important that you denote this by using a dot. For example, if we have a vector u and a vector v, and we wanted to find the scalar product or the dot product of the two of them, we would write in u dot v to show that. So please don't use the cross for this. There are two main forms for the dot product or scalar product, and we're going to look at both of them. It depends on what sort of vectors we're dealing with. Is it storage vectors, which we started on in our unit, or is it vectors in Cartesian form? Should be a capital C for Cartesian. Written as Cartesian vectors and not written geometrically, or is it geometric vectors that are drawn? Depends on how it's presented. So we need two forms to cover that. They're fairly simple operations, and it just accompanies what we've already covered, because we've covered vector addition, we've covered vector subtraction, we've covered multiplication, by a scalar. But multiplication by a scalar is not the same as the scalar product or the dot product. There are actually several types of operations with vectors that involve product or multiplying, so we must make them distinct. So it's a bit more complex than with just real numbers. So when we have two vectors that are undergone the operation dot product, the result, even though we have vectors going into the operation, the result is not a vector, it's a scalar, so a real number essentially. Alright, so the result is a scalar, hence the name scalar product. So it's two common names, scalar product and dot product, are quite logical. Dot product because of the dot used as the symbol, and scalar product used because the result is a scalar, or in other words, a real number. So getting back to the first form, we can use this first form when we have storage vectors, or we can use the same methodology with vectors in Cartesian form, which is, as you know, xi plus yj, and if it's three-dimensional it's plus zk. What we do, as the definition above says, is that we get the corresponding components and we multiply them together, and we keep going until we've finished. So the two vectors that undergo a scalar product must be of the same dimension, they must have the same number of elements in them. So if we have a vector A dotted with vector B, it's the first element of A is multiplied by the first element of B, and that is added to the second element of A multiplied by the second element of B, and so on until we get to the last one. The last one is denoted by n. Okay, and that's defined for those two vectors up there in general. So an example in Cartesian form, if vector A is 3i plus 2j minus 5k and vector B is negative I minus 3j plus 1.5k, what if we have to find A dot B? Well, again, we dot these two together, so we get the corresponding components in the first instance. Corresponding components of vector A and B in the first instance are 3 and -1. So 3 times -1, then we go 2 times -3, and -5 times 1.5. Important to get the coefficients correct, the signs of the coefficients. So remember, the result's going to be a real number or a scalar, so we've got -3 minus 6 minus 7.5. That comes out as -16.5, which is a real number, it is a scalar. Next we have another example with a real life context. This is using storage vectors, which is done very similarly. At a discount outlet, the prices in dollars of exercise books with those various numbers of pages are given by the vector P. Shows you the unit price of each of those books. So 32 page book would be 80 cents, 64 page $1.20, and so on. A student buys one 32 page book, 3 books of 64, 5 of 128 and 2 of 192. So write the student's purchases as a row vector and use the dot product to calculate the cost. Okay, you could do this of course without vectors, but this is just a simple example of showing how dot product can work. Defining vector S, and we're given vector P, so we really need to go S dot P to find our answer. So that's going to be 32 times 0.8 plus 64 times $1.20 or 1.2, and we continue on following the algorithm and we get the elements multiplied and then added as you see. We get 947.2, and because this is a real life question you should write $947.20. If we have geometric vectors, it's a different procedure. Geometric vectors, provided you know the angle between the two vectors, if we have the first vector v1 and the second vector v2, we have to find the magnitude of v1, we have to find the magnitude of v2. We go the magnitude of v1 times the magnitude of v2 times cos of theta, the angle between them. So that is written down here in an example. We have the scalar product of vectors. This one's an easy one, the magnitude is given to you, but you know how to find the magnitude of vectors from previous work. The angle is given as well. That one is a simple substitution. 5 times 6 times cos of 60 degrees is 15. The main variation on a question like this is if you have to work out each of the magnitudes yourself.